Okay. Started already?
No, waiting for you.
I was trying to bring more people, but I wasn't successful. People
No worries, no worries.
enjoy the sun and some more results. Okay. So we're gonna start. This is a more new methods tree, the third methodological section. We have three papers from Wu from Peking University, HSBC here in Shenzhen. It's gonna present first estimating non-separable selection models of functional current traction approach. 30 minutes.
Okay, I'm a just graduated from Caltech and I joined HSBC this year. I'm a theorist, and all my previous papers they do not have real applications. This is the first paper I've ever written has some real applications, and I'm very happy to present this work. So this paper proposed a new method to solve the sample selection problem, and sample selection issue occurs when the data is not representative of the entire population due to a non-random selection process. And this problem manifests in a variety of empirical settings. First, in empirical IO, we sometimes want to study consumer demand, but sometimes you want to understand how the consumer demand changed, given a change in price, or how the demand change when there's some cross-substitution patterns. But it's difficult to do this type of analysis because in the data, we only observe the consumer's transaction price. That is the price they accept, but we do not observe the competing offers in the data set. So we have a missing data problem. And secondly, in auctions, sometimes we, in the data set, we only observe the winning bids, but not all the bids submitted by the bidders. This creates a challenge because we want to use the entire bidding distribution to back out the bidder's valuation distribution. But if we only observe the winning bids, again, we have a missing data problem. And in labor economics, most classic problem, we want to understand how a worker's wage change given a change in their education year. But the problem is that I think I'm loud, quite loud.
No, but the problem is.
Oh, I see.
This is recorded on audio, so this goes into the system for the video for whatever we can listen in video quality.
Thank you. I need to lower my voice. With the classic labor economics problem, we want to understand how workers' wage changes based on change in education year. But the problem is that we only observe the wage of the workers who choose to work. And in the ROE model, we want to study workers' occupation distributions. But the problem is that for each sector, we only observe the wage distribution for those workers who choose to work in that sector. But we want to understand the counterfactuals. What if this worker were to choose a different sector? What if he were to choose a different industry? What would be his wage distribution in that industry? So again, we have a missing data problem. And you see in all these examples, there is this sample selection problem because there's a non-random selection process. And this is actually a concrete problem we face in one of our empirical papers for auto insurance. So in this paper, we want to study auto insurance companies' risk evaluation ability. So in this market, auto insurance companies utilize a strategy called risk evaluation pricing. What they do is that for each driver, they first generate a risk estimate, then price accordingly. And we want to study their risk evaluation ability, how precise they are at evaluating drivers' risk. But to do that, first key step is to recover each auto insurance company's offer price distribution because the offer price increase monotonically with their risk estimate. But the problem is that in the data set, we only observe each insurance company, their transaction price distribution. So again, we have a selection problem. And we want to recover the offer price distribution in a non-parametric fashion because the shape of the offer price distribution mirrors the shape of the risk estimate. So allowing for non-parametric estimation is critical. And here, we use the method proposed by this econometrics paper to recover the offer price distribution for the four firms I plotted over here. You can see that there are a lot of there's a lot of heterogeneities. These distributions, they vary in mean, variance, skewness, and whatever parametric structure you impose on these distributions, you are sure to miss many fine details in the distribution. So in this paper, we want to non-parametrically recover the outcome distribution before the selection occurs. Sometimes in literature, this is called the potential outcome distribution. And the previous literature tackles this selection problem in two ways. The first one is the most dominant one is leading by the classic Heckman's two-step approach. It typically imposes strong parametric assumptions. Suppose if I just assume the offer price distribution is Gaussian, then there's only two parameters I need to pin down, that is the mean and the variance. And the most advanced data art work is given by Arletta and Bahum. For their identification, they impose exclusion restriction plus some assumption called identification and infinity. They can get identification, but for the estimation step, they still need to put parametric structure on the copulus function. And another strand of literature tries to tackle this problem in a non-parametric fashion. But what they can do is only to recover the mean of the outcome distribution. They cannot recover the entire distribution. So we want to do it in a non-parametric way, but also recover the entire distribution. And we'll achieve this by constructing an operator whose fixed point is the true offer price distribution. And we show that it is a contraction in the functional space. And for the talk today, I will not be able to cover this part, but in the paper, if you're interested, you can read it. We also propose an estimator for the parameters in the selection model to establish consistency and asymptotic normality. By the way, if you want to read our paper, please hold on until the end of this month because we are making some changes right now as we speak. And compared to the classic two-step approach, we get stronger results because we make use of more information. It's not like we get stronger results for free. So for the standard two-step approach, they only need to utilize the first and second order moments to get the two parameters. But for us, we make use of the entire selected outcome distribution to back out the offer price distribution. So we may make use of more information to get stronger results. And one critical advantage is that we do not the exclusion requirements. We do not need the instruments that exogenously shift the choice probability. This sometimes is viewed as a critique for the classic two-step approach. Okay, because I'm a theorist, I will directly jump into the model. Here, for convenience, let's consider discrete choice problem. There's a finite set of alternatives, 1 to j. You can think of these as 1 to j sellers. They each sell a product, and each seller offers a random price, and this pi oj denotes seller j's offer price distribution. And for the talk today, for simplicity, let's assume everything continuous. We have continuous density, but for in the paper we can deal with arbitrary probability measure. But for today, just assume that we have a continuous density. And all the analysis will be conditional on some characteristic, observable characteristic x and some unobservable covariance x star, which we shall omit, but it is in the background of all the analysis. And we shall condition on enough observable characteristics and unobservable characteristics x star such that the offer prices, they are independent. This is almost like without loss because we can always condition on enough covariance to make them independent. And in our application, this x star also include the driver's true risk. Although in the data we do not observe the driver's true risk, but as geometricians we have the wisdom of hindsight. We can observe the driver's driving history, all their claim vectors. So this driver's true risk they expose estimable. And I collect all these pi j o and call this the offer price distribution. Here the O denote offer. This is the object of interest we want to recover. This we do not observe the offer price distribution. And a selection function f captures the consumer's choice behavior. Here, fj it denotes the probability of selecting alternative j. This function fj takes in a realized price factor and spill out a probability of selecting alternative j. Here, we assume this function f is smooth and it maps to an interior probability. And the summation of all these fj is less equal to 1, and this inequality allows for an outside option. This selection function is kind of an abstract way of modeling consumer behavior. I know it's not very standard econometrics way of capturing consumers' choice behavior, but let's connect to the more classic econometric approach. Here, for a simple illustrating example, let's consider two alternatives with an outcome equation. Here, the outcome is the price, and the potential outcome is the offer price, and the selected outcome is the transaction price. Here, this Pj is given by some linear terms on the dot is very small. P is given by some linear terms on the characteristic plus some error terms eta. This eta could be very well depending on x star. And we assume that we conditional enough covariance such that the price is independent once we condition on x and x star. And the utility is given by this uj. This gamma captures the price sensitivity, and this utility may very well depend on the other covariance x star. For example, like in labor examples, how the choice of selecting across different industries may well depends on this worker's productivity, which is hidden unknown. And this selection function f1 is the probability that one gives a higher utility. If we have a microfunction model such that the consumer always chooses the one with highest utility, and we can compare this with a more reduced form selection model. I can just plug in the price into the price term in the utility. So I plug in the price, and I can open the bracket. You can see that this is the composite arrow. You are very familiar in the econometrics literature. You see that this composite arrow in the utility term is naturally correlated with the arrow term in the price eta, because this term also contains eta, and this correlation and this XR will also introduce some correlation. So this correlation of the error term in utility and the error term in the price is the source of the sample selection problem. If there's no correlation between these two terms, then there will be no sample selection problem. So you see this framework, I forgot to mention that we can, in this paper, we can also allow for some separable errors. So we do not need this additive terms in the price. So this eta can be as a function depending on x and x star. So this is a very general framework that allows unobserved characteristics in the pricing function and also in the utility function. Okay, given the selection function, we can actually compute the probability of selecting alternative j only conditional on j's price. Recall that this fj is the probability of selecting alternative j given a realized price factor. If I only want to condition on pj, I need to integrate out against the randomness in the competing offers. And by the previous independence structure, I can write down the measure of competing offers as a product measure. Once I do this integration, I get the probability of selecting alternative j only conditional only on j's price. And given this object, we can compute, we can derive the density of the selected price distribution. For the talk today, I only need to use one tool, which is the Bayes rule, that you can understand everything. So this selected price density will be proportional to the offered price density evaluated at the same price multiplied by the choice probability of selecting alternative j only conditional on pj. Here I use this proportional sign because I'm off by a normalizing constant. And previously, I assumed that the selection function's this probability is strictly positive, which would imply that this PR function is strictly positive, which implies that this these two objects, the selected density and the offered density, they share the same support. So that's how we can recover the support of the offered price distribution. And this I collect all these pi s and denote it as the selected price distribution. This is the object we observe in the data, and we want to recover this pi o, which is the offered price distribution. And this problem at the beginning, I said I'm a theorist. At the beginning, for me, it sounds very scary in the sense that if you give me 10 equations with 10 unknowns, nonlinear system, I don't even know whether the solution exists or not, let alone solving for this system of nonlinear equation. You see, this system is also nonlinear because I have this multiplicative structure in the TR function. But here, the unknown, if there are 10 sellers or 10 alternatives, then the unknown are 10 offered price distributions. So the unknowns are 10 functions. And I gave you 10 functions that I observed the 10 selected price distribution. So I gave you 10 functions. I want you to spell out 10 functions. So now each unknown is an infinite dimensional object. So this problem sounds very scary for me at the very beginning. And let me give you a graphical illustration. Here I simulate some offered price distribution. This is what we want to recover. We do not observe this in the data. And if I'm a consumer, when I face a relatively low price, maybe I accept this offer with 90% chance. Maybe here price is kind of high, so I only accept the 50% chance. Maybe here with only 10% chance because I like lower prices. Yes.
Just a clarification. If you have the satisfy the best result.
Oh, so X star could include some unobservable characteristics. Okay, I just mentioned that I'm a consumer who prefer lower prices, so I accept these prices with different probability. But if you multiply this histogram by that probability I just mentioned, you will get a proportion of the offers that I accept. This is just a multiplication of the offer price histogram with the probability I just mentioned. And you see, and then I can normalize this transaction proportion to get a proper density function. And you see that this is a transaction price distribution we observe in the data. You see lower prices, they are overrepresented, higher prices, they are underrepresented. So we have a selection problem. And the exercise is that I give you 10, if there are 10 alternatives, I give you 10 orange histogram. I want you to give me 10 blue histogram. And like I said, we only observe the selected price distribution, and we want to recover the offered price distribution. And each object, this pi of s, is a collection of j probability density functions. And given a selection function, the cardinality of the unknown and the constraint, they are exactly the same. For now, let's assume we know this selection function. And the second part of the paper will tell us how to recover this selection function. But for now, let's suppose we know this selection function. Then the cardinality of unknown and constraint are exactly the same. 10 infinite dimensional unknown and 10 infinite dimensional known. And the key challenge is to solve for a collection of infinite dimensional objects in a nonlinear system. And at the time when I tried to tackle this problem, I only knew one tool that is powerful enough to solve this type of problem, which you will see very soon. Okay, so for the talk today, if you understand everything on this slide, you understand everything for the talk. Recall that we just compute the probability of selecting alternative J, conditional only on a J's price. This F is a selection function which takes in a realized price vector and spill out the probability of selecting alternative J. And once I integrate against all the randomness in the competing offers, which I integrate against the competing offers density product measure, I get the probability of selecting alternative J only conditional on J's price. And now we can derive the selected price distribution, which is proportional to the offer price density function multiplied by this PR function. This is simply this. Suppose miraculously I'm saying miraculously, if I know this PR function, then solving for this offer price density is child's play. I can just move this PR function to the left and divide by the price, then I get offer price distribution. Super easy. But the problem is that I do not know this PR function because this PR function also depends on the unknown. But the tentative approach is to plug in a conjecture, say any kind of conjecture, even like maybe like a uniform distribution. I can plug in a conjecture, this phi, which is the some conjecture offer price distribution. I can plug that into this PR function. Then I can replicate this exercise using this selected density divided by this PR function to get a new conjecture. And this operator T I just defined exactly replicate what I'm talking about here. Plugging any conjecture phi, which is a conjecture of offer price densities, get a conjecture PR function, and use the selected density to divide by this PR function to get a new conjecture. So this operator takes in a conjecture offer price distribution and give you a new conjecture offer price distribution. Let's check if my conjecture is correct. If the phi is equal to the offer price density, then this PR function would be correct. Would be the correct PR function. Then if by there's some randomness in this pointer. Then by the formula I write over there, this pi o would be proportional to this pi divided by this PR function. Then this object on the left, once I plug in the correct conjecture, this would be the true offer price distribution. Which means the offer price distribution is a fixed point of this operator. Then what remains to be shown is that this operator is a contraction in the functional space. So I start with the observe the orange histogram, the transaction price distribution, plug in a conjecture, get some conjecture choice probability, maybe here 90%, 50%, 10%. Then I divide my orange histogram by that percentage, conjecture percentage, I can get a new blue histogram. And I need to do some normalization, divided by some nasty, gigantic normalizing constant whatsoever. I can get a new conjecture. The blue histogram is a new conjecture. This is what the operator does. I'm a theorist. I like to talk about theory, but then I think that. So the main result will tell you that give you sufficient conditions under which the operator is a contraction in the functional space. I will give you an explicit bound on the modulus of the contraction. So here this rho equals to a quarter of j minus 1. Recall j is the number of alternatives, multiplied by the maximum of the price range. This pj upper bar minus pj lower bar is the price range of alternative j, multiplied by m. I call this mj, maximum semi-elasticity difference. It looks scary, but it's not. If you set this partial log f over partial p, this is exactly semi-elasticity. And I just replace this competing prices by another competing price profile, and to the difference, I take the soup over all the prices. So this is the maximum semi-elasticity difference. And the first theorem tells you that if this modulus is less than 1, then operator T is a contraction with the modulus less than rho. And by the Banach fixed point theorem, for any selected price distribution, we get unique offer price distribution corresponding to that selected price distribution. So we get existence uniqueness as a bonus. Moreover, more importantly, we have a constructive, explicit approach to recover the offer price distribution. You just give me any conjecture. You can even give me uniform distribution, and I can iteratively apply this operator on this conjecture, and eventually it will take us to the true offer price distribution. Let me give you a heuristic argument for why this would work. Let's just, for simplicity, let's just assume that I'm a super rich consumer. I don't care about the price. I take each alternative with 10% chance. I'm rich. I don't care about money. each alternative with 10% chance. If I do that, then there's no selection problem. Because this is like a purely random trial. Then the transaction price distribution will be equal to the offer price distribution, right? But in that simplified example, the selection function f would be a constant. The fj would equal to 10%. Doesn't care about the price. It will be a constant. Then if you plug in that constant here, the partial log f over partial p would be 0. This would also be 0. This would be 0. This would be 0. So modulus would be 0. Which means you get a super contraction. That's in one step you recover the offer price distribution. But this result says that actually that intuition could continue to work. It can be extrapolated around this the selection function, even if the selection function is not purely random, even if it is not constant, as long as you control this the selection function such that the selection function doesn't oscillate too much, then previous argument will still work, but now you need to iteratively apply the operator. It cannot take you to the true offer price distribution in one shot, but we will iteratively converge to the true offer price distribution. My advisor paid me to do this kind of illustration. He said, "Fan, you just said a trivial example would work, and the slight perturbation around the trivial example also work."
So have you have 3 minutes?
3 minutes, good. Let me give you an example. Actually, in our empirical application, this approach works miraculously well in the sense that in our example, our price range is around 1,000 euros, and the contraction operator actually converges around 4 to 5 loops. This is very surprising because I'm talking about contraction in the functional space. I'm not talking about contraction in the scalar space. So if an operator converges super fast, it implies that the modulus is very small. Now let me give you an illustration of why this modulus is very small for the classic approach. In the classic leading example. So in empirical IO, the most dominant selection function is given by this Loge model, and it's given by some exponent of price sensitivity gamma p plus some psi. From this psi captures some like branding, quality, loyalty stuff. And let's here I will give you an example where we have a lot of alternatives, but this semi-elasticity, maximum semi-elasticity difference is very small. Say if I have a large number of alternatives, to compute the semi-elasticity, I need to do this partial log f over partial p, right? I need to change p and see how the log f changes. So if I change pj, 2 terms will change. One is on the top, the numerator, one is in the denominator. And when there are a lot of alternatives, when I change pj, the main variation will come from the top because the bottom will be swamped by a lot of constants, this summation term. As a first order approximation, if only take into the top, the numerator, if I take the log will cancel out with the exponent, then I do the derivative, I would get minus gamma. But then I need to take the semi-elasticity difference. If I take the difference, this m will be close to 0. That implies why in our empirical application, the operator actually contracts super fast. And you might complain that it still looks kind of nasty because we have finite dimensional optimization problem. We have soup over a bunch of prices. Here, this formula looks kind of nasty because here I haven't imposed a lot of structure on the selection function. Here, the selection function could be very general. I only impose smoothness and interior probability. I don't have any other structure. So that's why this modulus looks kind of nasty. If you just give me one structure, which is called the log supermodularity, here I impose that this partial log f over partial p is modular, and in theory paper this is called log supermodularity. And if you just impose this assumption, then I can really simplify that modulus formula to give you a more explicit, easier bound. And with this, even your grandma could calculate the modulus with a calculator. And you will ask me what kind of selection function satisfy this assumption. Actually, the Loge model satisfied this log supermodularity, and the probing model with 2 alternatives also satisfy. But probably model with more alternatives, more than 3, may not satisfy. We have other examples, so you need to go back to theorem 1. And yeah, that's pretty much for today. Thank you. Thank you.
Yeah, if there is any questions, but you use all the 30 minutes, so you can chat with Van if there are any questions. So the second paper is going to be by Mengshan Xu from Mannheim.
Hello, everyone. This paper, okay, is this random?
No, the white one.
Oh.
Hello, everyone. This paper is titled as Policy Choice in Time Series by Empirical Welfare Maximization. And this paper is joined with Toru Kitagawa at Brown and Winnie Wang at Bristol. We want to answer. That's not fair.
You have to click on the slides.
Oh, okay, right.
Yeah, yes. Okay. Oh, yeah, I see. Yeah. Yeah, thank you. So in this paper, we study about the causal inference in the policy choice. We estimate we are interested in the causal inference as an economist, and we estimating the average treatment effect and of a different type. And one of the reasons that we are interested in that, for example, how the college attendance will change the future income. And here we study the causal inference of the college attendance. This is the one justified interest, but the other use of these things is that we study the current causal inference measures and to use that to guide the future policy choice. And this is the literature initiated by Maskey 2004 Econometrics papers, and they use this framework to link the causal inference and the planner's policy decision in the microeconomic context. And in this paper, we want to study the time series data and the link and the Mansky's approach, extend his approach to this time series context. And there's a lot of motivating example. For example, the federal open market committee's monetary policy choice, or the central bank's intervention of exchange rates, or the policy choice of relaxing or tightening the COVID containment policy. And taking the second example as a motivation, so the central bank might occasionally intervene the exchange market to stabilize the exchange rate, and given the time series observations in the past of the exchange rate, and the treatment intervened or not in the past and other controlling variables, should the central bank intervene today? That's mean we have to make a decision based on the past history to make a decision in the future or in the current time period. And we are assuming the treatment are randomized or we call the quasi-randomized conditional on observables in the data. And then in this paper, we propose this time series empirical welfare maximization, we call TEWM, to estimate the welfare impact of today's policy choice using the past single and time series data. And then we try to maximize this empirical welfare estimated, and finally we get a policy rule estimated to maximize our future welfare. And then we formulate the decision problem using the potential outcome time series and a study. And I'm going to introduce what is the potential outcome time series framework, and study the theoretical guidance and guarantee of the proposal in terms of welfare convergence. Let me first introduce some baseline setups. Assume we have a randomized the data or quasi-randomized data in an observational study. And the X here is the pre-treatment observed covariates, for example, education and previous earnings. And the W here, we use the binary variable W to indicate the treatment and random variables. And this treatment could be possibly conditional on X, for example, a job training program. And the Y here is the post-treatment observed outcome, like the future income. And the assignment rule is a function we call G, and based on the observable covariate X, and to 1 or 0, treat or not. And the Y1 and the Y0 to be the potential outcomes. And this additive utilitarian behavior can be presented by this equation. In this case, basically, we have an expectation of Y1 or Y0 depends on our choice. If we choose G based on this X, G equal to 1, we have a treated unit. If we choose G equal to 0, here becomes 0, then we have a untreated unit. So this is the expectation of the behavior under this policy rule. Okay. So our goal is that we, of course, this is the infeasible. Yeah. First, this is the population expectation. We don't have all the data. The second thing is this is a classical problem in any causal inference literature. So we cannot simultaneously observe Y1 and Y0, and therefore we have to somehow to estimate some counterpart of that. So then the goal of this paper is we try to estimate a policy rule G hat, and that performs well in terms of this behavior. And for the discrete X case and for the IID data, the Mansky's paper proposes what we call the conditional empirical success rule. And basically, he proposed to use this policy function where this tau hat is the estimated the difference mean estimator of the conditional average treatment effect. And then once this estimated average treatment effect is larger than 0, it's not negative, and then we decide to assign the treatment. And then Mansky assess this performance of this rule by bounding the what we call the expected welfare regret. So how to interpret that? Basically, this is the welfare, and this is the infeasible maximum welfare. The best policies here, but we don't know what is policy stat. So this is the maximum cannot be beaten. And this is the welfare evaluated under our proposed policy. Our proposed policies. Therefore, this one could be smaller than that one, but they have some difference. And this difference is called a regret, welfare regret. And the Mansky shows if you apply his rule, defined here, basically, once we have an estimated average treatment effect, conditional average treatment effect larger than 0, we treat under this rule, and then this regret will converge at a routine rate. So this is the Mansky's paper. And what we are going to do in this paper is to try to extend this framework to the time series, etc. Okay. So the question and the challenge we want to answer in this paper is the policy. We have basically 4 points. The policy impact can have a dynamic causal effect, and it can be heterogeneous and non-stationary. And this is also related to the problem of an external validity problem. And the second important one is that the observations are no longer IID. Of course, we have a time series data, so everything is dependent. Yeah. And then the third thing is what could be a reasonable welfare objective? How to obtain its empirical analog? And the last thing is how to obtain a comparable welfare regret convergence rate, and under what the condition, and what is the rate. And so suppose so this is some basic setup. So we have a social planner, and then we have a data is a single time series. Yeah, we observe the data of length of t. We call the first period time 0, and the last available on period is in time t minus 1. And then we have a YT, which is the observed outcome, and the WT is the binary treatment, and the ZT is the other contextual information. And then we denote the sample by this triple, x from time 0 to t minus 1, which is basically the triple of y, w, and z. And we have here's the important notion in the potential outcome time series. We have a treatment path, so which is no longer a single treatment, but which is a treatment history, which could be from the first period to the last period. And the potential outcomes indexed by this treatment path is given by this expression. We have a YT bracket, the treatment path, not only a single treatment, but the treatment path. Okay. Clearly, if we have a t period, so all the possible treatment path is like a 2 to the power t, and therefore we have a lot of treatment. Of course, we cannot deal with that much the choices. We have to do some sort of a truncation, some sort of truncation. Okay. So then here I will briefly introduce two important setup of the potential outcome time series initiated by Bizhinov and Shabas on just paper and Yambachin and Shabas paper. First, we want to assume that we have a non-anticipating potential outcomes, which basically says at each time period, the potential outcome only impacted by the past treatment, not the treatment in the future. So it is non-anticipating. And the second assumption is the very common assumption in the causal inference literature. We call non-anticipating treatment paths, but a more common name in the causal inference literature is the unconfoundedness. Of course, here we have a time-test data, so we call it, they call it the sequential unconfoundedness. That basically says if a condition on the observable covariate on the future treatment is independent to the potential outcomes. And so with this assumption at hand, we can construct our conditional welfare function, which is the object we want to maximize. And in this talk, I'm going to focus on this one period conditional welfare, where we have a conditional on observed covariate. And in the paper, we also discussed the unconditional version of welfare, which differs from that in the from the unconditional welfare in the cross-sectional setting. Okay. So to simplify the structure, we to show how to achieve the convergence rate of the conditional regret, we want to do some simplification here to simplify our framework to a toy model. Here we imposed this following two assumptions. The first one is the Markovian exclusion, which basically says instead of depends on all the treatment path, let our outcome only depend on the current treatment and the treatment in the previous time period. So we do some truncation. This is our first simplification. And the second one is the Markovian exogenarity, which basically says once we condition on the last period of treatment, and all the past history is no longer relevant. We do some sort of another type of truncation, basically, which means in the general framework, every conditional variable matters. But now, to simplify, we simplify this conditional variable to simply t minus 1, w t minus 1. And so by doing so, we can simplify the conditional welfare target with this assumption 1, assumption 2 to this one. Basically, our potential outcome only depends on the current treatment and the previous treatment, and the conditional variable is reduced to wt minus 1. Wt minus 1. So in these cases, we can somehow construct our empirical welfare, which is the feasible object we used to derive our policy choice. And so this empirical welfare is basically a simple analog of what we have present of this one. You can see we use this the average of a selected subsample to represent this conditional expectation, which basically TW here is that we're selecting those observation in the history which satisfy this condition. Yeah, in this condition. And then we have this is the classical inverse probability weighting type of a sample analog of the Y1, which is the Y0. It's Y0, physical version of Y0. And then we have our policy here to help us to select the decision. And then we have the ET here is the propensity score function, which is also in the causal inference framework to make sure if we have this structure, the expectation of this structure is actually the potential outcome Y1. So with this empirical graph available, and then we can do some kind of a calculation. But in the end, what we want to show is we want to show time series version of this convergence rate. This is basically the object of not the single object of that paper, but the object of my talk today. We want to show a time series version of this convergence. Yeah. So now we have already constructed this is the indivisible population version of the welfare, and this is the empirical version of the welfare. Yeah. Okay. So we need two additional steps to link this empirical welfare to the regret specification. The first one is we want to somehow construct what we call the intermediate welfare, which is basically we have a sample average structure, but we have the population level conditional expectation as a summand, and we put this, we decompose the condition, the empirical welfare into the sum of the psi plus this intermediate welfare, and then this psi will take the form of something, and this is a feasible the feasible welfare of a single period minus is a conditional expectation. And this one, this is not exactly conditional expectation, but you guys, if you take conditional expectation of this of the first term, this will equal to this one. Yeah, this is something what we want to construct. And then with this property at hand, I mean the formula in the middle of this display, we can show this psi is a martingale difference sequence. This is the key to achieve our convergence rate in the context of the time series data. Yeah, because we don't have IID, so we have to rely on some other convergence result in the time series context. And so after this construction, we show that the difference between the empirical welfare and this intermediate welfare, not the published welfare, is a martingale, is the average of a martingale difference sequence, and it will converge under certain assumptions. It will converge at a say root t rate. Yeah. Okay, this is the first step, and the second step is this is still one step away from our final target. Yeah. The second step is the assumption. So we want to assume this what we call the invariance of welfare ordering, which is basically an assumption link the target of our interest. The target of our interest is basically the left-hand side of this inequality, which is basically the optimal welfare minus the welfare under the optimal unknown policy minus the welfare under some arbitrary policy G. And then we want to impose this inequality such that the left-hand side is smaller than some constant times the difference evaluated with the intermediate welfare defined in the previous page. Okay, and this this condition looks a little bit non-intuitive, but actually, as we've showed in the paper, it can be satisfied by many structured time series model, including stationary or non-stationary time series model. Yeah, and particularly in this slide, I present one case which is also included in the paper that if we have these M2 structured models specified like this, and then that assumption will be satisfied with the sign of the coefficient of interest at time capital T, the last period, is equal to the sign of the average coefficient in the past, in the history, past history, which is satisfied this requirement. So this is the which means this assumption looks non-intuitive, but actually satisfied by many existing structure models. Right. And so then with these two steps, we can finally write down inequality. Yeah, we can finally see the regret between the optimal the welfare under the optimal policy and the welfare under the estimated policy will be upper bounded by this C times the regret measured in the intermediate welfare, and then finally upper bounded by this by 2 times C, the maximum G of this difference. And this difference is actually we've shown in the previous page can be expressed as an average of a martingale difference sequence. Yeah. So. And so then we can show this result. Yeah, we can show this result for the simplified model. Yeah, and basically the result is under imposed assumptions. The Mansk's C conditional empirical success rule can be generalized to time series, etc., and attain a roughly square root T convergence rate. Then we have of course, we're not satisfied with the simple models. We want to extend that to the case with more and the continuous covariate cases, which basically X can be specified as this one, as this one, and the conditional welfare is given by this formula where the X could be potentially multi-dimensional or continuous. And to do a similar derivation, we need some more assumptions. Basically, we define the unconditional welfare, which is the welfare without imposing a condition. And we assume, this is the key assumption for this case, so we assume the correct specification, which basically says that the maximizer of the unconditional welfare is also the maximizer of the conditional welfare. Yeah. And with this condition, and combined with the invariant welfare ordering condition specified before, we can finally achieve with some other technical details and omitted here. We can finally achieve a type of a convergence rate, which is roughly square root T up to a logarithm factor. Okay, so this is the major result of this paper. And we also have some extension to the infinite dimensional spar models, and which basically we need to rely on some sort of truncation. And this details is roughly summarized in this page. Basically, if we have an infinite dimensional and data dependence, we have to do some truncation, and the truncated part will become a bias term, and then the convergence rate is also contaminated by this bias term. So the idea of the reasoning behind is we rely on the empirical welfare. Therefore, we need to the scenario we studied for the current period need to be repeatedly observed in the history. And therefore, if there's infinite dimensional dependence, and then there's no similar history can be observed. Therefore, we must make some sort of a truncation to construct our empirical welfare. Okay. So in the last 5 minutes, I'm trying to briefly talk about the empirical examples. We study a COVID application, and basically the binary treatment is whether we relax the COVID restriction level, the W equal to 1, if we don't relax the restriction level. The outcome welfare is the -1 times 2 week ahead death in US. And the contextual information for the model of the propensity score, basically we include all this 1, 2, 3, 4, 5, 6 variables, and then we try to maximize the expected behavior of the set of quadro, which is basically threshold and policy rules, and based on these two condition variables. And the data is from the CDC website on Oxford Stringency Index and the Lewis Merton's stock business conditions for the economic condition. And this is basically a rough description of the data. We can say which is quite non-stationary. And then this is the estimation of the propensity score. We use the largest model to do the propensity score estimation, which basically means our model is not purely our model is majorly model free, but our approach is model free. But the propensity score we have to specify. If we use the parametric approach, then our approach is not purely model free. If you use the non-parametric approach, and then our approach is model free. But here, for simplicity, we use the large model to estimate the propensity score. And the things I want to emphasize here is you can say for this data set, and the estimation is quite well. We don't do any sort of a truncation, but it will automatically satisfy the overlaps condition for this cause inverse literature. So we have the estimators is larger than 0 and smaller than 1. By a considerable distance, and therefore we should not have this overlapping issue, and which is the commonly in the causal inverse literature. We don't have to do any truncation here to distort the data. And then this is the estimation result, which it basically said. So if the difference that is not going down, and if the restriction level in the last period it's not too high, we should not relax on the restriction level. This is the simple application of our proposed approach. And in our paper, we actually use a more complicated approach on the decision tree to including more policy variables. Okay, so then lastly, I want to briefly go through the literature. This paper is majorly motivated by the potential time series framework, which is including the paper for Angris, Jola, Korsteiner on the JBS in 2018, and also the paper mentioned already, the vision of Shepard's JASA paper and the Armachon and the Shepard's QE paper. And also this paper is also tightly linked to the treatment choice literature, including the initial work of the Mansky, and also many papers followed. And also our paper is related to the growing literature of individualized dynamic treatment regimes. But the major difference is this literature basically study the panel data. They have both large N and T, and usually they focus on the case with the large N and short T. And now we are focusing on the single time series, single time series. And so at the end, we also our work is also related to the empirical risk minimization in time series, including the Zhang and the Tanner's paper, ET paper, and also two papers of Brownings and his co-author. Okay, so to conclude, so we propose a framework of data-driven policy choice in the time series settings. We have to tackle non-trivial challenges and distinguishing the time series policy choice from the static IID1. And on the crucial assumption, the sequential unconfoundedness and the finite order Markovian and the invariance of regular ordering, the mask is the conditional empirical successful rule can be extended to time series. And we, with the correct specification assumption added, we can also extend it to time series with a continuous covariates. And our approach relies only on the causal and the conditional independence structure among the variables, and is free from functional form in general. And we don't impose stationarity, and we don't impose any prior distributions. Okay, that's all. Thank you. Any question?
All right.
Okay.
So the last paper going to be by Juan Paul from Toulouse. And talking about education policy and the quality of public servants.
Okay, hello everyone. So I'm Juan. I'm a PhD candidate at the School of Economics. This is my job mark paper, which is about how to use education policy to increase the quality of public servants. So the motivation is public servants are essential for both state capacity and effective public service delivery. However, the government struggles in the competition for attracting talent. Here I'm listing a few reasons. So there's rigid hiring rules in pay scales, limited performance-based incentives, and a scarce process for career development. And while it is true that for low-skilled workers, there tends to be a public sector wage premium, for high-skilled workers, we see the opposite, and they tend to face a public sector wage penalty, which tends to deter strong candidates. So research shows there are many policies that can improve recruitment, but in general, they are hard to implement at scale. So there's evidence that wage increases can attract talented people. In general, it's hard to implement a generalized wage increase due to fiscal constraints. There's also evidence of many different types of incentives-based reforms in which productivity is rewarded in different ways. And it's also successfully attract talented people. But in many governments, there are rigid rules in the public sector that makes these reforms unfeasible. So here in this paper, I'm the first one to take a step back and study the upstream role of higher education. So this would be policies at the higher education stage that seek to improve the pool of candidates that select into these types of professions. If we want to think how to design these policies and we look at the higher education finance literature, we will tend to see that it's mostly centered on equity and efficiency consideration, but whether scholarships can improve access and recruitment and the marginal efficiency of different funding instruments. But there's lack of evidence on what's the best way to design these policies to attract talent into strategic fields. So in this paper, I do three things. First, I will focus on a specific policy that was put in place in Chile that seeks to increase the quality of elementary school teachers by combining two specific tools in education policy. One is financial aid. The second one is admission standards. And this policy combined the two. I'll give you more details in a few minutes. So in the first step, I do an ex-post evaluation of this policy. Today, because this is the DSE conference, I'll spend more time on the second part, which is the structural part. But I will find that this policy managed to attract high-performing students at teacher colleges. It also improved teacher quality. But then I will exploit the variation generated by this policy, and I will study the optimal policy design, combining these two specific tools of education policy, financial aid, and admission standards, by building an equilibrium model of higher education that will allow me to decompose the relative influence of financial aid and admission standards in driving the third equilibrium. And then I can take into account endogenous responses from both students and colleges when moving away from the baseline policy into contractual policy rules. And then, if I have time, I'll say a bit about, okay, I find the optimal policy design, but then is education policy cost effective with respect to alternatives? Then with the model, I can simulate different variations of education and wage policies and compare the recruitment gains. Now, let me give you some context. So during the 2000s, there was an oversupply of students enrolled at teacher colleges, but they had problem of quality. So if you were an average student at the STEM degree, you would be a top 5% student at a teacher college. So you can see there the distributions of students at teacher colleges, at any program, and STEM. So they have too many students, but they have a problem with quality. So that's why the government wants to implement this two-component rule. So was established in 2011 in all public universities, but they made this policy optional for private universities. The reason to make it optional is that it was ex ante hard for the policymaker to know how to design it, and they didn't want to induce a closure of programs. This policy was based on the score at the National College Entrance Exam, which was a standardized score to enter college, and it had two components, as said. So, in terms of incentives, students will get full funding if they will score above the 8th percentile of this exam. And then for colleges, if they wanted to participate in this policy, they had to commit to impose a cutoff at the median. So in this setup, this financial incentive serves a two-sided purpose. So for students, it wants to induce self-selection, so because of the scholarship, into teaching. But for colleges, the idea of the scholarship is to induce this adoption of selectivity measures. So they have to trade off the extra enrollment they could get because of scholarship students against enrollment losses due to imposing admission standards. And in practice, take-up was low. 2/3 of these private universities opted out of this policy. And so this limits the impact it can have first because it limits the crowd out. If they don't take up this policy, they don't need to commit to this cutoff. And then there's less vacancies in the overall education system to attract students and offer them scholarships. And why take-up was low? So here I'm plotting the distribution of the test scores at different teaching programs. So the green area is the score you need to get in order to get the scholarship. And the red area is the score where you will be crowded out from teacher programs that take this policy. So for the top 10 teaching programs, the take-up decision was quite straightforward because they had barely any student who scored below this cutoff. So within this top 10, even the top colleges, the effective cutoff